Good morning. Can I please ask you to take your seats? Thank you. Good morning. My name is Eugenio Cantatore. I am the conference chair, and I would like to warmly welcome you at ISSCC 2023. ISSCC is celebrating this year its 70th anniversary, 70 years of innovation in the technical content, but also 70 years of innovation in the way the conference is made. We started in 1954 with the first edition in Philadelphia, to move to San Francisco in 1978, and at that time we had alternate venues with New York City. A few milestones of these developments include also the start of the Student Volunteers Group, the Saratoga Group, which is essential to our operations, the creation of several educational events, including the short course, the tutorials, and the forums, the addition of conference events such as the Student Research Preview, the demo sessions, the Women in Circuit initiatives. Finally, in 2021, we had to change our format to fully virtual. And this year, we are finally back to an in-person event with on-demand options. It is difficult to describe the joy in seeing you here in person today. Thank you very much. So this year, the registration count as of now is 2,854. The number that you see here is of yesterday morning. This is perfectly in line with the last ISSCC in-person edition that was in 2020. We have a record high number of students at 828. 84% of attendees are IEEE members, and 62% are members of the Solid-State Secret Society, the SSCS. 85% are in person, and 15% follow the conference on demand. 51% of registrants come from America, 38% from Asia, and 11% from Europe. A large number of institutions are present. Based on the data from 2022, we can estimate 306 corporations and 220 academic institutions. Being together in person, it will be great to network again, right? This is great value for us. In the budget for this year, we could accommodate 2 coffee breaks. There will be on Monday afternoon and on Tuesday afternoon. And 1 social hour on Monday at the end of the afternoon sessions. There will be no social hour on Tuesday afternoon. After the afternoon sessions, the traditional author interviews will be held. Several universities will organize receptions on Monday and Tuesday. ISSCC has worked intensively with the SSCS to provide additional benefit to the attendees. Wi-Fi is available in the ballrooms. The SSCS provided a Starbucks appreciation card in your registration package and a registration discount to its members. 34 travel awards have been provided to students, enabling them to attend ISSCC. Travel grants have been given to the winners of the Code on a Chip competition and to 8 students to attend the Circuit Insights. SSCS also provided 26 pre-doctoral grants. A total of 99 students thus obtained a complimentary registration. I'm now happy to announce that SSCS President, John Long, is present to this opening ceremony. Please join me in welcoming Professor Long to the stage.
Yeah, thank you very much, everyone. I'm John Long, President of the Solid State Circuit Society for 2023. And it's certainly my pleasure to welcome everyone back to the first in-person ISSCC in 3 years. It's really great to be back together again. And I'm going to make a few opening remarks on behalf of the Society. During the pandemic, I think everybody appreciated that publications from the Solid-State Circuit Society were really a lifeline, and a lot of people really relied on those more heavily than even pre-pandemic. So I want to just tell you about a few things that we're doing in publications that you might not know about and haven't seen before. Obviously, the Journal of Solid-State Circuits, the Red Journal, that's our flagship journal, and it's really the highest quality technical information for the engineering of solid-state circuits and systems on a chip anywhere in the world. But we have two other new publications I'd like to tell you about that you could look at. One is the Solid-State Circuits Letters. It's shown here in orange, but it's an all-electronic publication, not print, and it gives rapid turnaround in a 4-page format of the latest innovations in solid-state circuits. The other one is the Open Journal of the Solid-State Circuit Society. That's a new one, and that's for authors that need to own the copyright to their publications. And I'd really like to thank Eugenio Cantatore, who just spoke to you moments ago. He's the editor of the Open Journal of Solid-State Circuits, and he's done a tremendous job in bringing up that publication and getting it to the point where it's going to receive an impact factor and really take off. So thank you very much, Eugenio, for your hard work on that publication. I really appreciate it, and I think the Society really appreciates the work that you do for the ISSCC and for the Society. Now, conferences are the other big pillar of the Society. I think everyone knows that SSCS is very active in financially sponsoring conferences. We were created as a council and a society around the ISSCC many years ago, and the journal was created as a document of record for the conference. But aside from ISSCC, we have other conferences that go around the world. In North America, we also have the CICC. In Asia Pacific, we have the VLSI Symposia in Japan and Hawaii, and the ASSCC, which travels around Region 10. And in Europe, we have the SCIRC, which is teamed up with SDIRC and will merge together into one conference, not this year, but next year. So those conferences are sponsored by the Society, but of course our members get discounts for those conferences, as you know here. A thing that a lot of people haven't been taking advantage of, but which is really a valuable resource to everyone in this room, is the Resource Center of the IEEE. If you haven't visited it, the URL is there. You can go and take a look. And what you'll find in the Resource Center are webinars and videos, short courses from previous ISSCCs and tutorials from previous ISSCCs, and a number of other materials that would be of great interest to people that are designing solid-state circuits. For example, there's an excellent webinar on noise that you can get in the Resource Center that you won't find anywhere else. And if you haven't seen it, please go and take a look, because it's really a great resource for our members, and SSCS members should be taking advantage of that. Now, we do tease people outside of the SSCS with some of the materials that we have there on our YouTube channel. So we have a YouTube channel which you can go and visit. It's open to everybody, and we take some selected materials from the Resource Center and put them there. I've shown a few here. There's Democratizing IC Design, which I'll mention in a few more moments. There's a webinar from Professor Boris Merman. There's the Circuit Insights, which kicked off the ISSCC week on Saturday morning with the second Circuit Insights. That's an exciting thing for outreach to bachelor's and young graduate students. There's new materials, new innovations like artificial intelligence and their application to circuits that are there. And for career people, there's lots of information to help you build your career. For example, Women in Circuits has a great video on understanding work culture. So we have 10,000 subscribers on that YouTube channel. Please go give it a visit and see what you think. Now, I mentioned that democratizing IC design is a new initiative, and one of the things that we're looking to do as a society in our third function is education and outreach. And we recognize that we're competing with software, AI, machine learning, which are really soaking up a lot of the young people and their interest in science and engineering, and we're competing with that. And in order for us to succeed, we have to do a better job of reaching out to other folks. And the other thing that we're looking at doing is how we can get in contact with people in regions that we normally don't see. So many regions of the world, people know how to design chips, but they don't practice that art because they haven't got access to technology and the tools. So our PICO program, which is our outreach program, which was devised by Professor Boris Merman at Stanford and his team, is doing exactly that, using open source tools and open design kits from global foundries. And there are 2 chipathons that they've offered, and the Code-to-Chip travel grant that Eugenio mentioned previously. In the chipathon, the first one had 61 submissions and 11 chips were taped out. They got together weekly with these people that were participating on Zoom calls and taught them all the art of chip design and got them to the point where they were able to get their chips fabricated. And they got SSCS memberships together with that, and they got free fabrication. And that was a tremendous achievement by the team, but it also showed us that we saw people participating in this that we've never seen before. We saw people in Argentina, we saw people in Brazil and Pakistan. We saw folks in North Africa taking advantage of this. And it really was a great opportunity for those people, but it showed that we can reach out and we can have an impact around the world in a way that we never thought we could. And this is, I'd like to thank Boris and the team, and this is something that we're continuing, and we'll continue to build that, and I hope that people will get behind it and support this as an initiative of the society. Now, I think everyone knows that we have chapters. We now have 125 chapters, which is a tremendous achievement from our chapter team. Alvin Loke has been revitalizing our chapters. And for those of you that get involved with SSCS activities at the local level, the chapters really make a huge difference. You get in touch with students, you get in touch with your colleagues, and you work locally to build the society in a way which we don't see at international conferences. So get involved with your local chapter, make friends, and network with colleagues. It's a great experience, and it's something that I think we'll all benefit from. And last but not least, there's a big event at this conference that I want to mention. We have the Young Professionals and Women in Circuits Mentoring Session coming up on Tuesday in the Sierra AB room. That's on the 5th floor of the Marriott. And we're going to connect mentors together with young professionals, and of course, Women in Circuits Mentoring Session is also involved. So people can ask questions one-on-one, get advice from academics and industry leaders, and it's a great experience for those folks to be able to benefit from that. So if you have time, please stop by and offer your advice and participate in this session. So I'd like to thank the volunteers and professionals that have organized the ISSCC. I'd also like to congratulate the authors and presenters that are here and wish them luck with their presentations. And finally, I'd like to wish everybody an enjoyable and productive ISSCC 2023. Thank you very much for your time.
Thank you, John. Thank you so much. Thank you very much, John. Actually, I would like to show an additional initiative from IEEE Women in Circuits. It is a webinar called Unlocking Your Inner Leader, Strategies for Effective Managing and Advising. It will be held on Thursday, May the 11th at 9 a.m. PST. Please participate. Also, the IEEE Council on Electronic Design Automation has honored Dr. Giovanni De Micheli with the Philip Kaufman Award. A ceremony and banquet is planned next Wednesday, February 23rd, in San Jose, so it's very close by. You're welcome to register. But let's focus again on ISSCC 2023. So I would like to share you some very exciting highlights of our program. In analog, we will see area and power efficient amplifiers, new architectures and calibrations for improved accuracy of sensor front ends, and innovation to reduce trim points and improve aging resilience of frequency references. In data converters, we will feature time-based and hybrid pipeline SAR architectures, pushing the speed limits, and incremental converters with very high efficiency. Digital architectures and systems will showcase the latest high-performance industry processors, together with the innovative application-specific and IoT SoCs, and also advances in security processors. The Digital Circuits Committee will present advances in circuits for clocking and voltage regulation, application-specific accelerators to enhance performance and energy efficiency, and techniques that exploit emerging technologies such as non-volatile memories and wafer-level stacking of deep trench capacitors. IM&D features this year wearable and implantable applications that continue to evolve towards more intelligent, multimodal, and high-performance solutions, as well as closed-loop operation. Also, innovation in on-chip classification of neural signals, and from the imager perspectives, the advanced autofocusing capabilities in small pitch and large image sensors. Machine learning will showcase heterogeneous cores, allowing to tackle a diverse set of layers and compute needs at the expense of additional area, and computing in memory with different reconfigurable circuit modes, which make use of several memory technologies. The memory subcommittee will present SRAM-based computing memory, enabling from integer to floating point calculations. Power management features USB and computing power delivery with a number of innovative IC design that achieve high performance, minimum power loss, small size, and low cost. And in RF, you will find multi-core oscillators for low phase noise signal generation and millimeter wave frequencies, and also terahertz sources up to 0.69 terahertz. Technology directions will present interfaces for quantum computing platforms that allow increased speed and interact with larger number of qubits. Also, innovative platforms for integration of photonic and electronic functions on standard CMOS, and innovative circuits for monitoring and testing circuits during various stages of fabrication. Wireless features ultra-low power and high efficiency radios, taking into account practical challenges such as interference from sub-gigahertz to millimeter wave frequencies. And wireline will show power performance improvements of 100 gigabit per second electrical transceivers, together with building blocks for 200 gigabit per second and co-packaged optical links. This fascinating, exciting program was put together thanks to the leadership of Piet van Bach, the ISSCC 2023 ITPC chair. Piet works at imec, where he's presently fellow and is part-time professor at the Vrije Universiteit in Brussels. He has been member of the technical program committees of ISSCC, SCIRC, and AID. He has been SSCS Distinguished Lecturer, ISSCC Program Vice Chair, and RF Subcommittee Chair. Besides, Piet is among the 15 most contributing authors to ISSCC. Please join me in welcoming to the podium Piet van Bach.
Thank you, Eugenio, and also from my side, warm welcome. And the conference theme of this year is building on 70 years of innovation in solid-state circuit design. So as we turn 70, we will, of course, look back to the history of this ISSCC conference, but we will, more importantly, look into the future. And we have there seen that stimulating innovation is a very nice way to look into the future. So innovation, we have, more than before, we have used it as an important criterion to evaluate our submissions during the paper selection meeting. But we have also chosen to define from the beginning a dedicated session to innovation. And this is a session with 4 talks, and those 4 talks, they should give sparks to new circuit ideas in domains that today are outside the ISSCC box. I told you that we're also looking back to the rich history, and we do that with the nice commemorative supplement to the digest. And also, when you are walking in the corridor, you will see that there are some nice pictures of past ISSCC events. The functionality of the conference platform has been extended significantly over the last few years. And we are also using it now to evaluate, to rate the papers. So in previous editions, the paper ratings were done with the paper sheets, right, or with an app. So this is no longer the case. We will only use the conference platform. And so you see here an example of a paper that you can rate when you log in on the conference platform. You see at the bottom several stars. Let me zoom in a bit. And so there, encircled in red, you can give between 1 and 5 stars to rate the paper, and you can also add some comments. Then also I would like to draw your attention to the Q&A chat box. So there you can enter some questions. In addition, of course, to the live Q&A sessions or live Q&As after each paper, and of course, in addition to the author interviews at the end of each day. So you can enter your comments there. The authors, they will regularly take a look at those at this chat box, and they will start to answer after they have given the presentation. More than in the past, we are active on social media. You can follow ISSCC on LinkedIn, Instagram, and more will follow in the coming ISSCC editions, coming years. Of course, there is also our website, which contains a lot of useful information. Some statistics. The number of submissions this year was 629. And out of those submissions, we selected 205 papers. The acceptance rate was 32%, which is nice, in line with the historical trend. The breakdown is as follows. 22% came from America, 13% from Europe, 65% from Far East. 20% of those papers come from industry, 62% from academia, 6% from research labs, also including some papers that they made together with academia. And then also 12% of papers of industry in collaboration with other institutes. A closer look to the program overview. The accepted papers together with the invited ones are organized in 34 sessions. 2 of those sessions are invited. I already touched upon the invited innovation session from outside the ISSCC box, but there is also an invited industry session, which highlights digital processor and system products. So that's session 9. Then we have 12 tutorials, 1 short course, 7 forums, and today and tomorrow we have 4 evening events, 2 panels, 1 game, and then 1 special evening topic session. Yesterday there was the well-attended student research preview, and there was also a mentoring session organized by Women in Circuit. This year, again, we have our live demonstration sessions. They take place in the Golden Gate Hall, today and tomorrow between 5 and 7, and they contain 47 papers, 47 demos that correspond, of course, to papers which you can see in the conference itself. It's also important that you rate those demos. And also for that rating, we are using the conference platform. It's important to select the best demo award. So at the bottom you see a screenshot from the conference platform. At the bottom I've encircled the place where you can, onto which you can click to rate the demo. And when you click on that, a new window will open there in blue, and there you can enter your evaluation, give a score. So let me now show you the organigram of ISSCC. ISSCC is operated by the executive committee, chaired by Eugenio Cantatore, and then the technical program has been overviewed by me in collaboration with Frank O'Mahony, who is the ITPC Vice Chair. And then we have in total, the International Technical Program Committee in total comprises 171 members from the 3 regions. The Far East region and the European region, they also have their own committee. The Far East region is chaired by Jun Deguchi, and the European regional chair is Bruce Ray. And then the ITPC falls apart in 12 subcommittees. We have the Analog Subcommittee, which is chaired by Maurits Ortmans. We have the Power Management Committee chaired by Bernard Wicht. We have the Data Converter Committee chaired by Jan Westra. We have the Digital Architectures and Systems Committee chaired by Tom Bird. The Digital Circuits Committee chaired by Keith Baumann. Then the Imagers, Medical MEMS and Displays subcommittee headed by Ricky Muller. Memory is headed by Marvin Chang. RF by Jan Kranings. Technology Directions by Ali Ajimiri. Wireless by Che Ming Hung. Wireline by Johan Frans. And Machine Learning by Sukwan Lim. I also would like to thank a lot various people from different committees. So next to the Executive Committee and the ITPC, there is also the Committee of the Forums, short courses, demos, student research preview, ad hoc SSCS and ISSCC advisory group, the Committee for Awards and Recognition, publications and editorial, then also Women in Circuits, the ISSC staff, and then last but not least, the group of student volunteers who make this conference be very fluid without any hiccups. So I would like all members of any of those committees listed here to stand up to give them all a warm, well-deserved applause. Thank you all. Then some final announcements. No cameras are allowed in the sessions. Phone calls not allowed in the sessions, so please also put your cell phone on in silent mode. And please don't forget to provide your ratings for the papers as well as the demos. Also, the conference has a COVID-19 protocol. You can find it via the conference website, or you can find it directly if you take that link. And so now we come to the technical presentations of this plenary session. The first presentation will be given by Lisa Su from AMD. The second one by Akira Matsuzawa from Tokyo Institute of Technology and Tech ID in Japan. Then after the break, we will have Jo de Boeck from imec and KU Leuven, Belgium, to give the third talk, and then the fourth talk will be given by Erik Ekudden from Ericsson in Sweden. So it is my pleasure now to introduce Lisa Su for the first talk on innovation for the next decade of compute efficiency. Lisa Su is Chair and Chief Executive Officer of AMD. Over the course of her 9-year tenure as the CEO of AMD, Lisa Su has transformed the company into the high-performance and adaptive computing leader and one of the fastest-growing semiconductor companies in the world. She's an IEEE fellow, a member of the National Academy of Engineering, and was recognized by the IEEE with the highest semiconductor honor, the Robert Noyce Medal. In 2021, Dr. Su was appointed by President Biden to the President's Council of Advisors on Science and Technology. Lisa, you have the floor.
All right, good morning, everyone. It is a real honor and pleasure to be here today to help celebrate the 70th anniversary of ISSCC. And I think the amazing thing is just how much progress has been made over this time period. And it's also great to see everyone in person. It's been a long time to see so many of our industry and academia friends together. So my topic today is about high-performance computing. High-performance computing is something that touches all of our lives in many ways, and it's also what we as an industry and in academia and as an ecosystem are really focused on pushing the envelope on more performance, more compute, more efficiency. So, of course, I have to start with a picture. As they say, a picture is worth 1,000 words or tens of billions of transistors. But as we look at the progress over the last 70 years, you start with sort of the first pocket radio, which had all of 4 transistors. And then the last time I was actually here at ISSCC was actually 10 years ago. We were kind enough to invite me then. And in that time frame, we thought we were making a lot of progress. The state of the art, this is a notebook processor, had just over 1 billion transistors, 4 cores, 4 threads, 32 nanometer SOI technology. And we thought, that was pretty amazing. Now, how many of you were actually here 10 years ago at ISSCC? Actually, that's a pretty good number. That's a pretty good number. So all of you have together helped us get to what we have achieved over the last 10 years. If you look at the state of the art today, it's using a very advanced process technology, significant advanced packaging, chiplet architectures, so on and so forth. Now, this is a state-of-the-art server processor that has 90 billion transistors, 96 cores, 13 5-nanometer and 6-nanometer chiplets, and a lot of memory. So we have made tremendous progress over the last 10 years. And what I would like to say is that we have so much more to do. Everybody needs high performance and adaptive computing. If you think about all applications, whether you're starting from our personal devices and smart client devices, phones, PCs, tablets, all the way to, I know Erik is going to talk later this morning about 5G and communications and how that drives tremendous processing and horsepower, going to the cloud and high performance supercomputing and everything that we're doing with machine learning and AI. It's on us to continue the trends of increasing performance and capability. And I will say that we've made a lot of progress, but we also have a lot more that we need to do. So taking a look at some of the performance trends over the last decade, this is some data that we've collected, which looks at really industry data. So this is AMD, Intel, all of the processor vendors out there. And you can say that although there are some times that we are above or below the line, in general, we've been increasing the performance trends on the order of doubling every 2 to 2.5 years or so. That is with all of the conversation about Moore's Law slowing and all of the things like that. Even so, there's been tremendous amount of innovation on architecture, on packaging, on on increasing die sizes and on power, such that we're able to do that. So this is what we've seen, and that's the same is true for GPU performance. If you look at that over the last 10 plus years, you've seen a doubling of performance every 2 to 2.5 years. So there has been significant improvement there. Now, when you actually put it together, and I like to use this example because it's one of the hardest examples, which is high-performance supercomputing. And if you think about what we're trying to accomplish, we're trying to build the biggest computers in the world for solving some of the hardest scientific problems as well as business problems in the world. And this is how you see where is the state of the art. Like, how hard can you push technology to achieve advancement? And in this case, what we're plotting is over the last 10 plus years, the fastest supercomputers in the world. And what you see is actually, even though on the component basis, So our processors and our GPUs are doubling every 2.5 years. On a system level, when we bring out everything that we have, including much larger systems, much more parallelism, a lot more power capability, a lot more interconnect capability, we're actually able to achieve a doubling almost on an annual basis, which is actually pretty amazing if you think about it. Now, these are not cheap systems. They're not small systems, but they tell you what the technology is capable of if you really bring out every single thing that you know. We just recently passed a very significant milestone last year, which was the first exascale supercomputer. And you can see that there was actually a little bit of distance between that dot and the previous dot. And that exascale computer actually sits at Oak Ridge National Labs, and it's built in partnership between Oak Ridge, HP Enterprise, and AMD. It's using a combination of CPU and GPUs, lots and lots of technology in there, but we were able to achieve an exascale of supercomputing, both from a performance standpoint and, more importantly, from an efficiency standpoint. And now, as we all like to do, we draw the line. We draw the line assuming that, hey, can we keep that pace of innovation going? If we were to do that, what it would say is we would get to a zettascale, or 1,000 times more computing in about the next 10 years, 10 plus or minus. And so that's a challenge. That's a challenge for all of us to think through how might we achieve that. The other thing that's also very exciting that I think is touching all of our lives is just the rate and pace of AI adoption. So I'm sure that everyone in here has used ChatGPT sometime over the last 60 days. Is that true? Everyone? Not everyone's going to admit it, but yes. The truth is, this goes back to the insatiable need for compute. At the end of the day, we have this capability to make our computing much smarter, much more capable, and much more adaptable to the problems that we're trying to solve. But to do that requires that we build more and more powerful computers. So if you just think about these generative AI models, as you increase the number of parameters, your models get better. As you increase the number of parameters, you need much more compute to train and actually to infer as well. So another reason that we need to keep pushing the envelope on computing going forward. Now, I've talked a lot about performance, but the real thing that we have to work on as an ecosystem is actually energy efficiency, because at the end of the day, that is going to be the hardest problem for us to solve. And if you take a look at the same trends now on energy efficiency, and again, this is the same data that we plotted on the performance scale, what it says from an efficiency standpoint, using all of the best technologies out there, our efficiencies are not increasing at the same rate and pace. And there are many good reasons for this, and I'll talk about some of those. But this flattening of the efficiency curve actually becomes the largest challenge that we have to solve, both from a technology standpoint as well as from a sustainability standpoint for our ecosystem. So, taking a look at the same plot on supercomputing usage, if you look backwards over the last 10 plus years, you can see that we have gotten more efficient with our technology. So this is plotting gigaflops per watt versus time for those same largest supercomputers. But it's actually doubling in efficiency only every 2 to 2.5 years, which is different, right? So performance, we were able to improve much faster. Efficiency is actually being limited by some of the physical attributes. And if we, again, draw the line, it would say that for us to get to a zettascale, we would need the machine to be 500 megawatts. That's probably too much. That's probably too much. It's not practical for us to do that. It's on the order of what a nuclear power plant would be. And so this fundamentally says our challenge is to figure out how, over the next decade, we think about compute efficiency as the #1 priority. And there's a lot of work that has been done, that will be talked about in this conference, that's being done across the industry, but this is the #1 challenge that we have to continue the dramatic increases in performance and capability that we have seen. So some of the reasons that this is hard, and some of the reasons that we need to keep focusing on this. I have to say, process technology is still very, very important. I started when I was a student in process technology and device design, and it continues to be very important. But the fact is, Moore's Law has slowed down. It is becoming much, much harder to get density, performance, as well as efficiency. You can see over the last few years, we used to be on a trend of doubling performance about every 3 to 3.5 years. And as we get into the advanced nodes with 5 and 4 nanometer technology going to 3 and 2, we still see improvements, but those improvements are at a much slower pace. And so this is one of the reasons that the energy efficiency is a key, is slowing down. Another reason is, I/O don't scale. They don't scale the way our logic scales. We have made good progress in reducing energy per bit, but when you look at it from an overall channel quality standpoint, it's over much shorter distances. And if you think about our systems are getting much longer, much larger, this ends up being a power limiter as well. And then you look at memory, and we're going to talk a lot. I know you'll have in the session a lot of conversation about new memory, how we bring compute and memory closer together. It is also around the fact that we need more memory. These data sets are getting larger, and the bandwidth that we're requiring makes the memory access power another key area that needs innovation. So if you take a step back, what do we need to do over the next decade? It's really driving system-level efficiency holistically. So thinking about all of the elements across computation, across communications, and across memory that will enable us to achieve the most efficient systems. So one of the most important areas, and probably the area that we focus the most on at AMD, is efficiency through advanced architecture. And there are lots of techniques for doing this, but in terms of the highest order bit is that we want to use the right compute technology for the right workload. And if you think about this whole conversation about heterogeneous architectures or accelerated computing, that's really what we're trying to do. This is an example of that exaflop supercomputer that I mentioned is using MI250, which is one of our newest processors on the acceleration side, and it's exploiting a significant amount of architectural innovation, packaging, silicon trends, to really try to improve the efficiency over time. And so when you look at some of the components of that, it says that we have to focus on everything. And so, with MI250 as an example, it's a 6 nanometer GPU. It has significant new innovation when we compare it versus our previous generation at the same process technology. It has a lot more domain-specific architectural enhancements for both HPC as well as AI workloads. It has higher levels of integration with chiplets and a 2.5D integration, bringing high bandwidth memory close to the compute. And it has the traditional circuit design work that you do in terms of all kinds of power management, all kinds of ways to optimize the design efficiency. And you can see that each of those components is quite important for us to improve the efficiency of the overall solution. And I'll talk a little bit more about each of these components and where we think they really shine. Probably the largest lever in recent times has been the use of advanced packaging and the use of chiplets. You can see that there has been a very nice progression of both capability and payoff with advanced packaging, starting first with just two-dimensional MCM technology. This is the idea that you're going to use the right process technology for the right elements, and so you need your expensive, dense transistors for the computing elements, and then you need, let's call it less dense, maybe other capabilities for your analog and I/O capability. And what that allows you to do is kind of optimize. So that's sort of the 2D version. If you go to 2.5D, you can bring memory much closer to the GPU. It's very, very common. And then 3D triplets, I think, are just starting to take off. I would say that it's still early. The technology is still maturing for high volume, but there's tremendous capability when you can stack memory on top of a processor, or when you can stack logic on top of logic. You can see that there would be a tremendous capability here. And just as one example, what it really does is it allows us to bring the components of compute much closer together and reduce the cost of communication. So, thinking about when you had these compute elements on a board and how far they were and how much energy you had to spend communicating between them, now you can have them either on package in a 2D or 2.5D arrangement, or stacked in a 3D arrangement. And you see just a tremendous improvement in overall communication efficiency when you do that. So very, very promising, very important for us as we go forward. Another area that there's been a lot of work and will continue to be a lot of work is with domain-specific computation. This is the idea of using the right math for the right operations. So in this particular case, you can see that as we go from, let's call it your double precision floating point, to various other math formats, you just get much more efficient computing. And the killer app here is, of course, machine learning and AI and what we're able to do there. But it'll continue to be important. There'll be more specific acceleration that will be used for various applications as we go forward, because you can do this. And anywhere that you can do this, it will help us get more efficient in the computing overall. So when you bring all of that together, I want to give you one other example of what you can do at the architectural level. And now we take what was in the previous generation exascale computer MI250, and we introduce the next generation, which we call MI300, but this is the next generation of GPU acceleration for both HPC and AI. And you see that with 5 nanometer process technology, with 3D stacking, with actually stacking our cache and fabric die on the bottom, stacking the CPUs and GPUs on top, with new math formats, with a different memory architecture, you can see improvements on the order of 5 to 8x, whether you're talking about efficiency or you're talking about performance. I think that says a lot about what the technology can do if you put all those pieces together. Just to give you a little bit of a framework of what we're talking about, one of the more traditional ways when you think about how CPUs and GPUs work together, they each have their own, sort of memory cache, and as a result, they really can't share data across them without going through the processor again. When you use these new architectural capabilities in a stacked format, you can actually have a unified memory architecture, so that depending on what you're trying to do, what your next operation is doing, you can just take your data from a unified memory architecture, which just is much, much more efficient, right? So this is all about how do we get that last bit of efficiency going forward. So with that, we believe, architecture, particularly around compute operations, will have a very large impact on future efficiency. And from our calculations, we believe that we can be above the industry rate, even above our earlier projections from several years ago, by combining our architectural innovations together with chiplets and 3D stacking to achieve that. So that gives you one view of what you can do with architecture. Now, there are a lot of really smart people here, and I saw 800 plus students, and so we need you guys to help us with the next set of innovations. I'll talk about some of the ones that are sort of very promising as we look at it from an industry standpoint. I talked about the tighter integration between compute and memory. I think this is always going to be the case. As we think about what we want to do, it really is how do we efficiently connect the two. And so from standard DDR5 going to high bandwidth memory, going to 3D bonding, you can see a significant improvement in efficiency. Now, what we've demonstrated so far is SRAM stacking on compute die, which is great, by the way. We've put that into production, and it has a significant improvement in certain workloads, not in all workloads, but in certain workloads. But there's more opportunity here in terms of stacking, DRAM on compute, stacking other types of memory. Obviously, there's some innovation that needs to happen for that to be the case. But this is one area where there's a lot of opportunity for innovation. We also think there's been a lot of discussion about putting processing in memory. So as a processor person, that seems a little counterintuitive, but it makes a lot of sense if you think about it from a system standpoint. What we want to do is be as efficient as possible, and so there may be some processing operations that can be inserted into the memory, and this is some work that we've been doing in our research team with our partner Samsung, which has shown that with some insertions of some algorithms in the memory component, you can reduce the overall access energy by up to 85%. So also very promising. The work here is not just obviously on the individual components, but it's also how applications would use such technology. And so this is an area where a lot of cross-functional learning would need to happen. Also improving the efficiency of I/O. I saw that, Pete, on your list of many things that are being worked on this conference. We believe that a lot of work has been done on sort of the local communication. So a lot of the chiplet work, advanced packaging work, does very well on local communication. But a lot more needs to be done on the longer reach I/O capabilities. And so, optical communication is a key area that we think is very, very important for us to reach anything like a zettascale type computing capability. There's a lot of work that's going on at this conference. We've also been doing some work with DARPA on how to do some of these co-packaged optics solutions as well. But what we like to say is that this is the view of sort of a future system in package. So one of the things that we are starting to really embrace as an industry is that the package is sort of the new motherboard. You used to put all of these pieces, taking all of these pieces from different vendors and different technologies and putting it together on a board. Now what we have to do is ensure that there's a way to put all of these different pieces and all of these different capabilities in a package. And what that does is that requires us to think differently on many levels, right? Certainly from the compute standpoint, our goal would be to optimize every one of those compute cores to be the best they can possibly be. So whether it's a CPU or GPU or a domain-specific accelerator, whether you're going to use an ASIC to do some machine learning, either training or inference, you can have each one of those compute cores be optimized, but they should be able to be optimized by different people. So this whole importance of standardizing chip-to-chip interfaces such that we can mix and match components, I think is very important. And then we talked about, adding, sort of co-packaged optics that can then go across the system overall. And all of this is made capable with, our advanced 2.5D and 3D packaging. So there's a lot of work that needs to be done to enable this, but it is surely doable as we, focus on the right elements of both, very clear optimization within each of our specialties, as well as ensuring that there are good enough standards for us to connect to across the different components. So now let's go back to our how do we achieve zettascale computing. I would say that I'm not sure we know yet. I would say we have very many pieces that we talked about. We'll continue to want to push process technology. We continue to want to push architectural optimizations. We'll continue all of the chiplet and memory and interconnect things that we can see today. And we believe that that will significantly enhance our overall efficiency. But if you really think about it, there's probably still a gap because of all of these physical limitations that we talked about. Whether the gap is, an order of magnitude, or it's less than that, or more than that, it's kind of hard to predict right now because there's still a lot of technology innovation to go. But I think it's fair to say that there's still much more we should do in terms of focusing on energy efficiency going forward. And so one of the key things that we should consider is leveraging AI much, much more holistically. And you can think of AI as a solution for, sort of very repetitive problems. And that's the, sort of the training of large models and things like that. But you can also think about AI in much more of a hybrid mode of operation. And just taking a look at the relative performance over the last 10 years, as much as we've improved in sort of the traditional metrics around spec-int rate or flops, the AI flops have improved much faster. And they've improved much faster because we've had all of these mixed precision capabilities that we've introduced there. And so the point is, how do we now use this much more broadly across a number of different problems? One that we're looking at and we think is very important is the idea of AI surrogate physics models. And the thought process again is how do we use the right type of compute for the right problem? And so this is one way of thinking about it. When you think about some of the most complex physics problems that you have out there, how do you solve it? Yes, you can get a big supercomputer and you can run your CFD models and do that with very large data sets. That's the traditional way of doing it. But much more, this concept of AI-accelerated HPC is also a very interesting lever, which is the idea that you might do a part of the physics capability with traditional HPC computing, and then you actually train on that data, and then you can infer on that data so that you can shorten the cycles. And then you might not be at the right answer yet, and so you would go and train on a different set of presumably a smaller subset of the modeling. And so this is more of a hybrid workflow. It's early. There's a lot of work to be done in the algorithms here, and there's a lot of work to be done in just how do you partition the problems. But this is a huge opportunity for us to bring now much more algorithmic thinking into our system-level optimization. And if you think about how we get to some of these numbers, we have to do that. So when we take sort of the overall picture. I think the key point, and for all of us who are here, maybe it'll be interesting to see what do we say at the 80th anniversary of ISSCC. Do we have some new elements to talk about? But certainly, if we look at everything that we've talked about, there's significant work going on, tremendous innovation. It's important that we bring it all together to solve large-scale, system-level problems. And AI will continue to be a more and more important piece of that, whether you're talking about some of the algorithm work that I talked about, or actually even how we use AI in our design environments to design faster and faster chips, reducing time to market, improving the capabilities. There's a lot of leverage there. So let me finish off by saying, again, it's really an honor to be here. I like to think of coming to ISSCC is like coming to talk to the smartest people on the planet, and so to leave you with anything is really an honor. There's a few things that we should feel really good about, right? We are probably in the most exciting time there is for technology. I certainly like to say in the computing world, everybody needs more compute. Like, people used to ask, well, do I really need more? The answer is yes. You need more and more and more because you can see how much smarter we can make everything that we do and how much more efficient we can make our lives. Even if we have someone who's, I guess for the academics in the audience, you probably don't want your students writing their papers with ChatGPT, but they can probably at least start with it, and then they could make it much, 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 much better because they can spend incrementally less time on the things that are most differentiating. The primary thing that we have to deal with for those of us in hardware is energy efficiency. That is the primary limiter, and that will continue to be the challenge that we should all keep in front of us. We must also innovate in new dimensions. Anantha asked me to say just a couple of words about some of the work that we did as part of PCAST. We were fortunate enough earlier last year to spend some time on what should be sort of the 5 to 10 year vision for the U.S. around semiconductor R&D. And I think the major point is we need all of our disciplines to work very closely together. There isn't one bullet is going to help us get to the next point. There is architectural work to be done, there's materials work to be done, there's systems work to be done, there's process technology, circuits, and the more that we can bring these together in turn to solve large problems, large grand challenges, as we like to say, because it brings out the best in the industry and the academia ecosystem when we point to something. So whether it's how do we get to a zettascale faster, or how do we take our current chip design and reduce the time to design a chip to 1/10 or 1/100th of how long it takes? Instead of 1,000 engineers, can we do it with 10 engineers? Maybe not. But those are the types of problems that, as we think about them, will cause us to come up with the next set of innovations. So again, thank you very much for having me here today. It was a pleasure to be here. And thanks for all that you're doing to keep moving our technology forward.
Thank you, Lisa, for this excellent talk. The next talk is an excellent combination of looking back in history and looking forward. It is in the field of mixed-signal circuits, and I'm delighted to introduce Professor Akira Matsuzawa, who will give this talk. He is Professor Emeritus of Tokyo Institute of Technology and CEO of Tech Idea. So Akira Matsuzawa, he received a Bachelor, Master of Science and PhD degrees in electrical engineering from the Tohoku University in Sendai, Japan in 1976, 1978 and 1997. And in 1978, he joined Panasonic. In 2003, he joined the Tokyo Institute of Technology as a full professor. And in 2018, he became Professor Emeritus and CEO of TechIdea. He has been developing video rate ADCs, mixed signal SoCs, and millimeter wave CMOS transceivers. In 2022, he received the Donald Peterson Award, and he's an IEEE fellow since 2002. Matsuzawa-san, the floor is yours.
Thank you very much. Thank you, Chairman. I'm Akira Matsuzawa. I would like to talk about shape the world with mixed signal integrated circuit, past, present, and future. So next, where? Okay. Background. Firstly, celebrating the ISSCC 70th anniversary. Congratulations. I'm also 70 years old. So, okay. Maybe I am one of top oldest ISSCC people. So my life is perfectly with ISSCC. Okay, so in the past, the 15 years, many analog devices have been replaced by two digital ones: audio, TV, video, camera, communication, and so on. So many mixed signal integrated circuits have been developed to contribute to the progress of this digital equipment. So aim of this talk is showing how mixed signal IC contributed to create new application field and how it progressed, and discussing the future progress. So this is the content of my talk. So I would like to introduce you the created digital system with the relationship of the mixed signal integrated circuit. And later, I will discuss about the future progress of this technology. And another subtitle is Learn from the past for the future. Okay? The feature of mixed signal integrated circuit is we can use both analog technique and digital techniques. So many variety of technique we can use. First is digital audio. Compact disc CD was released in 1983, and this is the first commercial digital equipment. And it required 16-bit, 20 kilohertz bandwidth D2A. First commercialized DAC used high-precision bipolar circuit and thin film transistors. Okay, and this is a thin film nickel-based thin film transistor, and using the laser trim to ensure the 16-bit accuracy. This is very high precision, but low productivity and somewhat expensive for the consumer use. So currently, audio DAC use a delta sigma modulator that can suppress low frequency noise using this architecture. Before the quantization, integrator is located in front of a quantizer, and using a negative feedback, that forms this transfer function. So we can effectively reduce low frequency noise using this method. However, in the initial stage, there was a problem of instability. So the instability issue can be solved by the cascading the first order integrator termed MASH. And basically, delta sigma modulator can express the analog value using a 2-point pulse density modulation. Okay? However, the output of the MASH is 5 value. So express this value, firstly use pulse width modulation with a stable 2-point voltage. So mismatch free. However, the issue is sensitive to the jitter, timing jitter. The voltage modulation is less sensitive to the jitter, however, very sensitive to the resistor mismatch. So conventionally, DAC select these elements from the left side. This is a conventional use of the DAC, and this accumulates the error. So to address this issue, data-weighted averaging method is developed. This is a rotates element. So using the method, the accumulate error from 0 to full scale becomes 0. So this method is very powerful solution. And using this method, we can increase dynamic range, in this case, 12 dB at the same clock jitter. So we now use this method for the digital audio. So we create the digital audio. However, recently, some young people like more analog, fast analog LP record with a vacuum tube amplifier. So I asked him why. Oh, Professor, sorry, this sound is somewhat solid. I reply, I'm sorry, I developed it with a solid state circuit. Okay? And also, he said, the sound is very warm, very, very warm. Oh, this is because the sound is heated by the filament in a vacuum tube. So the sound is warm. Okay, this is a joke. Not scientifically. Next, digital TV. The development of HDTV started in the second half of 1970, very, very early. This is because practical broadcasting of the digital system it started at around 2000, too much long time to develop. So firstly, that use Muse method, such as using 2 foldings to suppress bandwidth. So, and this is a very early stage HDTV and board at around 1989. So this is very old, and later HDTV system has changed to the MPEG base. In the second half of 1970, the issue is video rate ADC for encoding and decoding the TV signal. Only available video ADC is a board using many hybrid ICs, and very, very expensive, amazingly. almost same price as a car. So of course, not suitable for the commercial product. I joined Panasonic 1978 and started to develop the video rate ADC. And we developed a monolithic 10-bit video rate ADC, flash ADC at 1982. So this used a very high precision bipolar comparator. It could reduce price and power 10 times lower compared with such an ADC board, but not enough. So later, at around 1990, BiCMOS could be used for sample and hold and two-step flash ADC to reduce the circuit size, theoretically 15 times smaller size and power. The issue is a large error caused by the mismatch between the two conversion range, like this. So this issue could be solved by introducing the interpolation architecture like this by using this circuit. So as a result, we can realize a very smooth AD conversion. This is because the interpolation method realizes like a suspension of the car. So the reference area is like a spring coils, expand very, very adaptive. So at that time, we couldn't use a digital calibration. So the architectural solution is a very important. Next is the handy camera, camera recorder. Camera recorder, handy camera recorder, recording and playback the motion picture into the analog magnetic tape. So at around 1990, a handy camera recorder using a digital technology was developed to stabilize the image caused by the camera shake. So moving vector should be detected and correlate the correction the image by change this field memory address. So the portable system has a strong motivation to use digital technology. Still, the issue is ADC. So portable system requires low power ADC, in particular the CMOS. But still, that is an issue. So we developed the CMOS video rate ADC using a chopper inverter and a capacitive interpolator. And the capacitive interpolator can reduce the effect of the mismatch down to 1/4. And also, this gray inverter can be removed to further low power consumption. The energy, conversion energy of the video rate ADC at around 90, this red circle, red dot shows the CMOS, and the blue box shows the bipolar. So at that time, CMOS is not necessarily the low power compared to the bipolar, but we can reduce power 1/8 using this circuit and architecture technology. So this success of the ultra low power CMOS ADC triggered the emergence of the low power electronics. So we organized the low power electronics workshop in 1995 in order to aware the importance of the low power consumption. So low power technology created portable, wearable, and implantable devices. So this is one example. This is our developed wristwatch type PHS communicator using a Nagano Olympic game in 1998 using our developed low power DSP. So it is very advanced device. So most of my students like this development rather than the integrated circuit. Maybe that is very cool. Other example is co-developed wireless PDA using FD-SOI. So this PDA can operate with natural energy such as heat of the hand. This is a wireless PDA. So, and published ISSCC 2003, very early. So low power technology has become the major stream of integrated circuit. Up to that time, only high-speed, high data rate with power-hungry circuit is preferable rather than the low power. Next is imaging. The first practical solid-state imager use CCD method, charge-coupled device. CCD is an amazing device that can transfer the control, the bulk potential, noise-free transfer. Amazing. The charge transfer to neighbor by periodically change the bulk potential. So in CCD image sensor, optically excited charge are firstly transferred to vertical CCD with vertical CCD and horizontally transferred with horizontal transfer CCD. And voltage is converted to the digital and in external ADC. That is conventional use pipeline ADC. This is because the pipeline is very fast and reasonable high resolution bit number. So CCD imager was the first mass production for the application of the pipeline ADC. Of course, the pipeline ADC later and used in many electronic devices, such as base station in wireless communication. And pipeline ADC make the folding characteristics like this, and along with stages progressed, more finer folding can be made. So the very high scalability for the resolution, so widely spread. But the basic issue of the original 1-bit pipeline ADC is nonlinearity error. If voltage is jumped from the conversion range due to the comparator offset, the linearity is deteriorated. So very, very low offset comparator is required for the original 1-bit pipeline ADC. That is a very serious issue. So perfect solution is given by this 1.5 redundant architecture. The folding point is sufficiently inside of the conversion range. So offset no effect to the linearity. So this is a very perfect solution for this problem. And other issue is nonlinearity due to the low gain of the op-amp. And high gain is required for the higher resolution. So this problem is solved by the development of a gain-boosted amplifier in a cascade circuit. So after that, and the pipeline ADC is widely spread to use. Currently, we use CMOS image sensor. So CMOS image sensor use active pixel. The accumulated charge in a photodiode is transferred to the floating diffusion capacitance. And source flow buffer the voltage, and output is converted to the digital by the inside of the chip and the column ADC. So to cancel this KT over C noise, firstly transfer the reset signal, and next transfer the pixel signal, and to make the CDS correlated double sampling to cancel the KT over C noise. So we can use a smaller capacitor to increase sensitivity. And due to this parallel ADC, column ADC, and the data rate can be increased. Conventionally, column ADC use counter-based ADC, narrow width and low power and good monotonicity can be achieved. And to reduce fixed pattern noise or correlated noise, CDS is made. And firstly, use this switch and to form the analog CDS to the reset signal. So next is digital CDS for the reset signal. And after settling, the pixel can be converted by the ramp signal. Okay, so this system is very, very this system is very robust to the fixed pattern noise. So, and we can enjoy the very clear image by using this method. So recently, image sensing is spread to progressed to the 3D imager and measure the distance. Like this. So by using time information, and also to improve the quality, voltage information also needed. So VCO-based ADC is very smart. This is because this ADC can generate time information as well as voltage information simultaneously. So the imager now widely spread, and we can use imager conventionally used in smartphone. So this imager may form the society for the more democratic society. Next is recording. such as HDD and DVD. With increasing the recording density, ISI is inter-symbol interference becomes serious. It reduces amplitude of the signal and shifts the timing. So conventionally, in the past, HDD and use some threshold processing. However, no longer can be used. So late 90s, this method is applied. And this is searching the most probable data using this equation, the distance equation. This is the data, expected data, and this is the signal strength. So searching the most smallest data series. So this is called the maximum likelihood method, and this is widely used. So high-speed ADC is needed to determine this signal strength. So high-speed ADC saves the crisis of the recording HDD and DVD. So recently such a maximum likelihood method is widely used. Okay, so this story tells us the importance for our life. This is because don't seek the perfect. Seek the most probable action for your happiness. Okay? Life contains many errors, so no perfect. But the error can be corrected. And this is the digital read channel in DVD system. So, and the pickup signal is very unclear and very contains much error. And data out is reconstructed using this ML method. So high-speed ADC is required, even though that is a consumer product. So further, in addition, in 2003, we developed the one-chip mixed signal SoC for DVD system. It can integrate whole DVD system, and that can reduce the number of the chips and components and board size, the consumed error, and production cost. So the mixed signal SoC realizes ultimate system integration and big stream for integrated circuit design. Wireline also suffers the ISI. The increasing the data rate, I doesn't open due to the high attenuation at the high frequency. So this method, ADC with DSP, is used. In particular, for the very long-range optical communication system that use X polarity and Y polarity. However, along with longer distance, the two signal is shifted, and constellation is overlapped. So DSP, such as a 100 gigasample ultra-high-speed ADC, is used with DSP and compensates this effect and obtains a clear constellation. So this is due to the such a dispersion effect in optical fiber. So high-speed ADC can be constructed with highly interleaved SAR ADC. And SAR ADC is very simple and small and low power, so it can receive the full benefit of the technology scaling. So the interleaved SAR ADC with DSP realized the intercontinental internet with optical fiber. Wireless communication, due to the Shannon theory, higher data rate requires not only a wider bandwidth and also high SNR. So the advanced ADC always required. And furthermore, the signal is not only baseband, but also IF signal or RF signal. So ADC reaching the antenna. In future, maybe antenna, only use antenna and ADC can make a receiver. Continuous time ADC has a special meaning for the wireless system. This is because in wireless communication, very large unwanted signal blocks the weak wanted signal. So filter circuit is required in front of the ADC. Continuous time ADC that use a continuous time integrator has a filter function and can reduce the burden on the filter. So recently, the bandwidth is very wide, such as 465 megahertz using a mesh architecture. So wireless communication, in particular the base station, requires a high dynamic range and wide bandwidth advanced ADC. So this is one example for RF sampling, such as interleaved pipeline ADC can realize a 12-bit and 80 gigasample and high-speed conversion. Also, continuous time pipeline ADC also realize the wide bandwidth and high dynamic range. And another interesting application is, in a wireless system is beam forming. The phase of each element can be tuned by the dark and quadrature modulator. We can focus in the beam with the arrayed antenna and direction to enhance the signal power in the air. This is one interesting application of the mixed signal technology. Future progress, mixed signal neuron circuit for AI processing, the MAC operation is a core of the AI, and this requires the resolution, not so much high resolution. So we can use such an analog method. In this case, using capacitive DAC, the energy efficiency is in analog is tens of times higher than the digital. So, and other is CIM computing in memory system. Each memory cell, in this case SRAM, using a capacitive DAC, and also in this case use ReRAM. That is very resistance is programmable. So this SIM make a very efficient AI processing. Quantum computer needs such as a microwave transceiver for the spin qubit, and also array of the D2A for controlling the potential for a single electron qubit. So, and operating temperature is very low as 1 to 4 degree K. So cryo-CMOS technology become important for this application. Recently, analog computing method becomes important again for AI and quantum computing. When I was a university student, I couldn't use a digital pocket computer, only use this analog slide rule. Okay. So I'm very old people. And so, but time is not linear. Not linear. Time is like a curve. So again, we use analog computer after the 50 years later. So the fusion of the analog and digital circuit for a future computer is a very exciting challenge for us. So direction of the ADC, the hybrid ADC using decision voltage for pipeline and delta sigma is gaining the momentum. And we still need amplifier. We still need the amplifier. So recent interesting amplifier is a ring amplifier that use phenomena of the oscillation, and also the floating inverter amplifier that can separate the power supply from conventional VDD. The biggest issue is the sampling of the signal. And large capacitor is required to reduce KT over C noise. So it causes, one issue is input current, peak current is very high. So difficult to drive the ADC. So recently, continuous time pipeline ADC is developed to address this issue using analog delay line. So other issue is energy consumption will increase with increasing SNDR. So recent interesting work is KT over C noise cancellation ADC. That can cancel the KT over C and can use more smaller capacitor. And also the energy consumption becomes small. So this is a very fundamental research. The performance and progress in ADC is advanced, such as conversion energy is advanced, and also figure of merit is advanced. So ADC performance progressed consistently. In conclusion, mixed-signal integrated circuits have contributed to the development of the new system, and the popularization and progress with cost reduction saves the system crisis, create the new computer system such as AI and quantum computing. Further progress will be expected. Last conclusion, learn from the past for the future. For example, high precision device and circuit to circuit solution and architectural solution for with low precision device. So high speed device and circuit with large power to highly parallel low power and small size for high throughput. And high SNR and error free to low SNR and error correction. That is in progress. So we are very happy. This is because we have much work for the future. Okay, and enjoy the circuit design. Thank you.
Thank you very much indeed. It is now time to move over to the next part of our program.
Okay. So yeah, since 1986, he's with imec in the headquarters of imec in Leuven, Belgium. He has been a NATO Science Fellow at Belcor, USA in 1991 and 92, and AST Fellow in the Joint Research Center for Atom Technology in Japan, 1998. In his research career, he has been leading activities on integration of novel materials at device level and new functionalities at system level. He held various management positions at imec, including Chief Technology Officer. In 2018, he was appointed imec's Chief Strategy Officer, and he's also part-time professor at the KU Leuven. Jo, the floor is yours, and the clicker is yours.
Thank you, Pete.
Good morning. I had challenges before, but giving a speech during a break was never one of them. Thanks for being there. I appreciate your standing, so please keep standing up. That's good for your health. I'd like to get your attention, and that's going to be my challenge for the next 30 or so minutes. Thanks for the committee to invite the presentation on the European CHIPS Act. There's many CHIPS Acts ongoing, as you know. The European version of this is going to be the essence of my talk, but it's going to be, in general, give an insight and opportunities that we see. And this is, thanks again to the committee, a co-authored paper, which is quite unusual for a plenary. So I'd like to thank my colleagues from France and Germany. Fraunhofer, Letty, and imec have been shoulder to shoulder to talk to, for instance, the Commission and all of our friends in the research community and the industry to try to find out what is a good plan for Europe. And as this evolves, because it's not finished yet, I'd like to give you insights in what the opportunities are, not as much the politics of it, but the opportunities for you as a community. And this really is a family. I mean, I was here at 2011 on this same stage. I feel like coming back to the family. I'm a bit of an in-law, though, because I'm a technical hardware and physics person more than a designer. My last design was on 3.5 micron CMOS with Hubert Amman, so that dates way back. But this is the time where design and technology need to come back. And I was pleased to hear John say that the SCIRC and SDIRC conferences will be coming together as one conference. Maybe IADM and ISSCC should do the same, because there is quite a need for doing this convergence, and that'll be part of my discussion today. Needless to say, and we've had the pandemic to emphasize it, semiconductors can be key and will be key in tackling challenges of the future. One of the challenges is moving all of us from point A to point B with the same impact as a refreshing bike ride. The other one will be to make sure our industry produces the things we really need with the input and output that is sustainable for the planet. Healthcare needs to be at the quality of the future in places where medication has not arrived just yet for all of us on the planet. And then doing this in the transition of the Green Deal, making sure that what I mentioned before is done with a footprint as small as possible is going to be the essence of all we do. And semiconductors can be of help, but before we do this, we need to reflect on ourselves. And I'm glad to make a bit of a shameless commercial for the panel of 8 o'clock this evening, where we will talk about a sustainable ecosystem for the semiconductor industry. And what we are doing with our partners, and this is happening worldwide and at a very fast pace, the industry and research community is coming together to make sense of and to model and fully understand in this, for instance, virtual fab model, how we can do a sustainable manufacturing for integrated circuits. This is just scope 1 and scope 2. There has to be, of course, quite a broader look at how semiconductor technology will impact the future. And one way of doing this is to fundamentally understand the manufacturing process per se, and how to change the way we work with new materials, how we process them into our devices, and how, in the end, the waste of this process is being reused or recycled. Actually, coming here and flying back to Belgium takes me about 5 wafers of 28 nanometer. Just to say the footprint of wafers is quite humongous. And if you go to more advanced nodes, well, you could say the good news is you need fewer wafers, but the impact is, of course, going through the roof if we don't take care of managing and risk mitigating this. So we'll talk more about that at the panel this evening at 8 o'clock, so please feel free to join in. Since we're talking about Europe, I'd like to make a few reflections throughout the presentation, but this is one that has been in one of the studies, and I'll show quite a few studies during the presentation. This study showed the share of Europe's global electronic systems production, so what we consume in Europe that contains chips, if you want, or the data that goes with it. And you see in some areas, to zoom out a bit, zoom in a bit rather, you see in some areas Europe is in the lead, or at least in a relatively high position compared to the rest of the players worldwide. So you see automotive, aerospace, you see industrial, healthcare, and a few others, and then of course you see the numbers go down quickly. It's interesting to see in the embedded and would say professional area, that's the red bars below, the presence is quite high. In the more consumer or standalone applications is way lower. So this shows already there's a bit of an imbalance of what Europe likes to have and also what we produce. For instance, in the insert you see here, there is a 10% presence of the value chain, roughly, could be single digit depending on the study you look at. And there's a 20% need. So this deficit in how we use semiconductors and how we produce them is in Europe, it's very visible. That's also the supporting argument for doing the European Chips Act. This is another way of looking at Europe's presence in the whole of the value chain. You don't only see the semiconductor manufacturing right there in the center, but also the chip design, equipment and materials, and I'll show a few examples. There is some strength in Europe as well. But then, of course, EDA tool and materials and wafers are less of European presence. Interesting statistics or interesting facts, as a matter of fact, here to look into and to understand why Europe has come up with a plan. And so a bit more than a year ago, President von der Leyen and Commissioner Breton, showing off here a 300 millimeter wafer, emphasized the fact that Europe needs to do, as the other regions do, put more effort and emphasis on getting back in the race, if you want, and to make sure that the strengths that we have in Europe continue to be strong and thriving, but also that gaps we have, we fill in by strong collaboration. I'd like to emphasize that strong international collaboration is going to be important, but also making sure the gems we have or the training we need to provide is going to be there in the coming years. So this is the plan. How does it look? It has, as you will find here in the US or in other places, for instance, Japan, different sets of activities that need to be tackled. First and foremost, capacity for innovation needs to be built. A lot of training will have to go with that. Capacity to innovate, that means that not just the talent or the infrastructure, but broadly speaking, the whole of the community, the full stack needs to be engaged. And then, of course, more production is going to be enthused in the European setting. And so their incentives for more manufacturing are in place. And then, of course, training the workforce. It's useless to make these plans if you don't have the people to execute on them. And one of the more contentious ones is, of course, to make sure that we understand the full supply chain, and actually, from a political point of view, maybe even influence it. So that is something that's under a very strong debate. So how do we foresee the disruptions of the supply chain that we have managed? One element of the CHIPS Act, and that's the first, is on the capacity of innovation. And we know that the technology is moving fast, and we've had references in the morning already to technology, either being at analog or digital, and a combination of both. That is in need of many more experimentation and actually piloting this to maturity that you can get the design community to engage in these new technologies. imec is one place. You have Fraunhofer, Leti, and a few other research and technology organizations in Europe, which are quite strong in providing the technical backbone, say the new devices, the new integration facility for doing this type of early experimentation to the level of maturity that you can start doing these engagements. The engagements go through the whole of the ecosystem. And I think that's one of the strengths that we realized over the past decades. That is, if you can bring the materials and the equipment providers into the fab, because that's where they are, and then connect that to the IDMs and the foundries, but also to the fabless and the design community, and to the systems and the OEMs, that you can build a very, very strong
network of innovation. You can start seeing the roadmap in action in your ecosystem. And that's, of course, what's quite important, to make sure that all of the insights are being captured. We've been doing this for decades in these RTOs, but we are now calling out, and that has been done this morning as well on stage, to make sure that this comes together even stronger in the future. Let's start at the equipment and the materials and the device architectures, because I'd like to give you at least a little bit of a flavor of where these new devices will go. And Lisa has shown in the morning that there is going to be a need of more devices, but she also showed that the speed and the pace of how they will push circuits forward is sort of flattening. But there is still a relentless need for making these devices and the circuits go to dimensions that have not been made before. And one of our partners at imec, a strong partner since the 80s, is ASML, that of course, as you know, is leading the pack in how patterning or lithography is done. Here's one example of the 14 angstrom generation that we have in the fab today that takes into account not only the patterning part, but also new materials, the fact that you need to build these devices in a gate-all-around structure. And that is a feat that is very hard to accomplish if you don't have the full slew of integration facility at hand. The future is still bright or challenging, at least in terms of scaling down, and that is what you see coming up, and the new generation of tools that will allow this scaling is the high-NA EUV tool, which is currently under development. It's a European strength there that is not only something of one company, it's really a network of suppliers, a supply chain being very, very strong, not only on the tool, but also on the materials that are used for doing the resist, but also for later on making sure that this patterning becomes a device. How these devices will look, again, also there is a roadmap, and we are very familiar in this industry with road mapping. It is continuing. We'd like to see ahead a couple of generations, and this easily can be a decade plus, as you can see, not only in how the shrinking will happen, I showed the example of high-NA EUV coming up, but also how device architectures will change and how the context of connecting these devices to each other and to the rest of the circuit is changing as well. This roadmap is a hard one to realize. Let me show one example of, say, the fork sheet transistor, which has been shown in the fab already, which is the next generation in the angstrom family, if you want. But even then, next will be shrinking that fork sheet to something which is called a complementary stacked device, where you have the different layers stacked. And that means that new technology for manufacturing this device will need to come into play. This will require very thin body layers to be stacked on top of each other, and it actually opens the era of going really in 3D for transistors. And there will be much more to come, which it's not even shown on the roadmap, where the third dimension will be very, very important for the devices of the future. As I said, not only just on the cartoons, we already are making these type of devices in the fab, because to show that it can be done, although making them at pitch and making them yielding is, of course, something that will take a number of years to come. And also contacting them, as I said, is going to be one of the issues, because you'll need to bring this logic plane that you can then manufacture with these new devices or with the current generations of devices. You bring this in a full system on chip. And again, Lisa showed very nicely that this combination of different different functionality will allow systems to become much faster at a much lower energy. And this combination is essential for future technology. So this SoC in its full complexity will need technology development as well. And as I said, this is ongoing, and it will need further elaboration in the coming years. But we can connect die to wafer, we can go backside power delivery, and this is already a new paradigm also for the design community. So here's one example where technology development needs to go hand in hand with the design tools that will allow the designers and the architects to partition the system over these different functionalities and to use, for instance, the new function of backside power delivery as the technology provides it. How to bring the design community here, and that's where the higher maturity of the pilot lines can help. We can go into virtual PDK mode. We can try to deliver in silico tested models that you then, as a designer, can use for doing virtual prototyping. We can then combine this with functions which are already there, emerging memories, optical I/O, 3D stacking of other chiplet structures and functionalities, and build, maybe even first in the model and then in the first demonstration, new ways of doing SoC. It's happening in large companies, but we need, for the training aspect also, academics to get very, very quickly access to this. We also need to train ourselves as technologists in how we can use our new tricks to really help the design community to do what it needs to be done. And there, of course, the connection to the final application will be needed. A very strong plea also to understand the workload and bring this down to this type of virtual prototyping. It's a challenge. It's something that only in a very broad full-stack innovation approach can be realized. A good example from our French colleagues here in doing this, and have been done over the past decades, is how to bring this ecosystem together. Fully depleted SOI is a very nice example of, from the technology, the materials, over the IDM and foundries, to the use case and the design community, and then of course also supported by quite a lot of research. This will continue to thrive at least a couple of generations before it sort of marries with the gate-all-around technology that is on the roadmap that I showed earlier. So a lot of synergies are to be found in the coming decades. Fully depleted SOI will find its position in many of the markets where the benefits that are shown on this slide will be crucial for success. Of course, power and energy efficiency is often the first thing to look at, but then again, analog performance and robustness are two other features of this type of technology. And will it scale is a challenge that we are facing together, because as I said, a lot of generic questions need to be addressed. And so here is a scaling looking forward, which is also positioned in the European Chips Act as one of the important elements of future development. And so, as I said, there's a lot of technical challenges needed to be solved, but there's also the markets that need to adopt this. And the markets for this particular technology, as we've seen over the past decades, is going to be forward-looking, more or less the same, like changing the way that circuits are doing mobility, that you have Internet of Things, that you can think of the implementation of fully depleted SOI in 5G and in the mobility devices as a whole. So this is what we'd like to push forward together with, again, the full ecosystem. And this makes fully depleted SOI a very interesting building block in all of the other sets of building blocks that we can bring together for this system on chip. So chiplets has been mentioned before. This is another animation of the one that you saw before, the non-break, bringing together, for instance, the photonics, bringing together the logic, bringing together memory, bringing together also elements of the legacy nodes, fully depleted SOI, as I mentioned, but also RF components and new material systems, because I've been talking about silicon most of the time now, but we know 3.5s in many functions and functionalities will become very, very important for RF and power, and a few examples to be given later. So just to drive this message home once more, the future of innovation will require system-level thinking, will require to bring the workload, the algorithms very, very close to this type of development platform. How to do this is really build that synergy. And in the European Chips Act, the plan is to also have a design platform to be developed and further elaborated to make sure that there's a cloud-based system that can connect the existing foundry technologies or IDM technologies that can be in the general offering, but also to introduce the new functionality that I just mentioned and are being developed in these pilot lines. Let's make sure this becomes an international collaboration, but first and foremost, let's make sure the platform is there, and that's part of the action that is currently being taken. On design, because I'd like to shift gears a little to this audience, training is going to be essential. And Europractice, for I guess quite a few of you know this, is a very nice system to connect the academic and small and medium-sized enterprises to the technology nodes which are offered commercially out there. It has, and this is the 2021 data of designs that have been ported through the Europractice program on the foundries, and you see a very large presence of the analog and mixed signal and almost non-existing presence of the leading edge nodes. I was privileged to use the data of Professor Willy Sansen here. He looked, as you know, over the ISSCCs over the past decades at what the contribution of these different nodes and the different functionalities are in this conference. 2021, quite a strong effort on analog and RF, some digital, the nodes, of course, being more on the relaxed side. You see, 5 years down the road, introduction of new functionalities, new materials, FDSOI, FinFET coming in, so the more advanced nodes peeping around the corner here. 2022, moving even further into the advanced nodes, but again, a very, very strong presence of course, the legacy nodes in all of the analog and some of the digital functionalities. Interesting to look at, also to realize that moving design to the leading edge, or bleeding edge if you want, for academics and small and medium-sized enterprises is a no-go just because of this. So we need to find a way to train people, because that is going to be the essential part, train people also in these leading edge technology. And talking about people, there is one slide for sure I wanted to show is how do we see the STEM community, our youngsters, coming into our industry. That is a concern. And Ingrid mentioned it. Congrats, Ingrid, by the way, on the award. She mentioned it. It's very important to reach out to the community to make sure that the higher level education, master's and PhD, but also the bachelor or tertiary level STEM comes into our semiconductor industry. Interesting here on this slide, and you've been looking at it for about 10 seconds now to try to make sense out of these figures. We still see, of course, if you look at the total tertiary STEM education, China is leading the pack. But if you look, and this study shows a bit of an optimistic note for Europe, if you look at the master and PhD level, over 400K students are being trained in Europe. So I think our continent has something to offer to also this community to make sure that we can get them enthused in for instance, design, but also technology. So this is just one of the many, many data that you've seen on shortness of skills throughout all technical education and industry. Let's make sure we understand how we can do better for our industry in design and technology. Because it's a very nice era to live in if you're in this industry. Because again, of this convergence of design, use cases, algorithms, and technology per se. And so I'd like to give a few examples of this in the remainder of the presentation, showing how this system technology co-optimization can be done and where some of the opportunities are clearly in the offing. One is, of course, in compute, and there is a very heterogeneous set of computing coming our way. Of course, the high-performance compute, a few other notes on this later, but also quantum. I saw one of the highlights was in that arena. Let's make sense out of the quantum in the coming decade. Neuromorphic for certain elements, but also, of course, the very, very distributed version of compute that we need. You can ask the question, what will be the impact of AI in all of this? And yes, of course, you should ask ChatGPT first, right? So this is what ChatGPT makes of it, and it's not complete nonsense, indeed, so there are a couple of interesting elements. But of course, this engine can only do so much, and the more of the size of the model in the future, the better and the more precise the answers will be. This is, and actually it's been shown before again by Lisa, there is a tremendous need for more size on the model. And GPT-4 could be on the order of 500 times more in size and, of course, in challenge in how to realize this. This is the central compute. It has its own challenges. It goes, of course, for accuracy. It builds on this homogeneous network. Well, that may change in the future, as we learned earlier. And it will, of course, drive for the exponential increase in operations per second. But how about bringing some of that functionality to the edge? If you'd like to do this in the edge devices we know today, you need a roughly said 15-fold faster processor and 170-fold bigger battery. That'll be non-manageable for this type of AI implementation on the edge. We'd like to make sensor fusion, personal touch, making sure that these type of intelligence comes closer to the edge. And I think the best example to use there is how to get sensor fusion and the digital functionality of artificial driving into a robot like this one. Challenges are in many places here, and this is one example of the three I will show. Automotive has, of course, the electrification part. A lot of analog needs to go in there. A lot of new materials need to be introduced because we'll be banking on 3-5 semiconductors for a lot of the functions there. But if you look at autonomous driving per se and the complexity that needs to be tackled there and the connectivity that the car has internally and to the environment, the mature nodes and the leading edge will need to work together there. There will be a fusion of the activity of both of these types of devices, as well on the communication part. So I think there are going to be a central infrastructure or architecture in the car, but it's going to be part of this distributed system. Some things you will learn in the car while driving because it's needed for the latency. Some things you will feed into the cloud to make all of us aware of better driving opportunities coming forward. So this is important. Again, it's going to be a combination of these sensor functionalities, power device functionalities, and of course, the digital part that needs to get all of this together. If you look at, again, a study of the trends of circuits in automotive, evidently here again, legacy and mature nodes will require a lot of innovation and will be present in a car even more than today. So going forward, that's the lion's share of the circuits that you'll see, but you see the compound annual growth rate of the most advanced nodes are there as well. And that's, of course, a challenge for our OEMs because they are used to work with their tiered system in bringing in the mature nodes and the innovation there. They're not so sure on how to take in the leading edge opportunity and how to build a car or an HPC on wheels. And that's a challenge not just for the design part, but also just for the energy, because unless you're willing to spend a third of your energy on the compute and sense, and hence have your distance of driving cut significantly, we will need to do something on that energy consumption. The numbers are staggering, the challenge is enormous, but if we don't, we'll run up in burning too much energy for just having the function that we need. There could be neuromorphic in there, right? So there could be spiking neural nets making sense of radar data in the sensor, for instance, then feeding that back into the central engine for doing the sense making or the information translation. That could be one element, but it's one of the many. And so if you look at from the real device point of view, making these new devices, I mentioned fully depleted SOI, there's going to be leading edge components in there. So from the dark triangle of the fabs and the labs in technology up to making these platforms, like, for instance, 3D integration will be needed, bringing the chiplet revolution to automotive, doing backside power delivery circuits even if needed. So all of these technologies will require to be developed also for this application. And then, of course, on the algorithmic side, you need to make the sensor fusion become really a reality. And so that is where we see a lot of the current activity where, again, requires a lot of input from many different disciplines will be needed to make a difference, and how to then build with all of this a sort of digital version, a digital model of the car that will manage our driving, that will manage the way that we do mobility in the future. This is where the opportunity lies quite a bit, because even if you, quote unquote, just design a circuit for one functionality, you'll need to keep your eyes open to how it impacts the rest of the function of the robot. In this particular case, the car. Same holds true for robotics in general sense. Second example, and we'll hear more about that in the next presentation, will be beyond the 5G era. Also, there is going to be quite a bit of combination of technologies, because it's driven, again, by the same need of data bandwidth and connectivity. More numbers in the next presentation, I'm sure, but just to give a flavor of, again, where the opportunity of combination of different technologies and design will come in. Let's take the one, and again, that also has been mentioned and quite nicely explained in the previous presentation, beamforming when you go to millimeter wave. Stepping away from the single antenna, making sure that you have a cohort of antennas working together to make the steering of the beam become reality. Work on that is, of course, happening. We see challenges, you see challenges on the way there, challenges on the CMOS efficiency, doing the RF, challenges on the packaging and integrating passives on the system and miniaturizing the whole system. Of course, challenges on the beamforming per se, on the digital and the analog side of things, and making sure that we can bring in the most complex DSPs for doing the function, because a lot of this, of course, is digital. More in the next presentation, again, I'm sure, but this gives us as technologists quite a choice or a challenge again to bring in the right material, because not all of this will be done by CMOS. Quite a bit will be done by 3.5s, and 3.5s that need to be co-integrated very, very intimately with the rest of the functionality to make the whole system at the right size and at the right cost point, because also that is going to be a challenge. The cost point for 3.5 semiconductors is a challenge because they are typically not made today with the standard processing or the advanced processing that you'll find in silicon. Often they don't need it in terms of size and patterning and density, but often, again, the cost point will be dominated by the way you manufacture these. And for instance, we're looking at gallium nitride on silicon as one example to make use of, to say, the 200 or 300 millimeter facility that has been matured for silicon, to use that for instance, gallium nitride. And the same type of efforts are ongoing for the other 3.5s, which is quite a challenge. But you can do it. You can, of course, make these circuits independently and then bring them together. I think that's where the next generation of circuit design and system innovation is definitely coming. We as technologists make sure that this combination, again, can be done at the right size, right dimensions, and the right cost point. System technology co-optimization, once again, also in this arena, is going to be essential. Architecture partitioning, and actually also having the design tools at hand to allow you to do this. And this is where, of course, the EDA community is going to be a very, very strong partner for all levels of modeling that need to be there in order to make such a compelling circuit. Last but not least, and I see the orange is on here, so I'd like to make the use case for health and life sciences. That, as a matter of fact, was my 2011 presentation on this stage. Technology will move to health. Well, what has happened over the past decade has been an enormous change in how silicon silicon-related and semiconductor technology is quote-unquote helping the clinic, helping the medics, helping the university and other hospitals to take in this very early technology and turn it into something which has many facets of innovation, from restoring biological function, bio-inspired storage for our community maybe, making sure that synthetic drugs can be made. Now we can sequence DNA. Can we do more in synthesizing? For instance, human brain interface or human machine interface in general. These are all domains where a lot of this currently is happening. Many other conferences of the same size here are focusing on this type of technology and innovation from the use case point of view. How can we treat certain pathologies? How can we administer in the future therapies, which will be very much more personalized? How can we do synthesis on the spot when needed? And again, all of that will be used by not only technology, but also, of course, the data that goes with it. But on the technology side, again, here, that stacking or that complexity is happening. We can use standard, quote-unquote, foundry wafers and use our tricks in the clean rooms to add functionality that you could not imagine previously. And of course, to the end, it'll go to microfluidics because you need to make contact with the biospecimen, cells, DNA, RNA, proteins, etc. And so that whole toolbox is waiting to be harvested. And of course, a lot of innovation needs to be done, but there are a few things already that we can do quite nicely, as long as we understand the need. And it's easier to understand the telecom need, maybe, as engineers, or the automotive need. It's quite a bit harder to understand the need of the clinic and the patient. So that's what we and many of us in this community have been investing in over the past to make sure that this full stack, again, from materials up until the impact it has on us is important. And here's one example. We are building models on certain pathologies. In this particular case, it's Parkinson's, that we try to bring on a chip, because we can actually, by tailoring the real function of the cells, which can be done through stem cell and reprogramming these on chip, we can try and actually working in this particular case on making cell structures which are a good replica, more or less, of what is happening, for instance, in the brain. And this brain-on-chip type of effort is good because we can do tests on the silicon in vitro that we then cannot never do on humans. So this is to understand the disease and further on, of course, to mitigate its impact. DNA sequencing, past decade has made a humongous efficiency increase based on the fact that we, for instance, here can use, as I mentioned earlier, a standard CMOS wafer, put some filters on top, and a nanopore, for which we, of course, need the most advanced technology to make this in a very parallel fashion without the variability that would be detrimental for this. So very highly precise parallel functionality, in this particular case, an example of Pacific Biosciences, that worked with us to build this particular DNA sequencer, which not too long ago helped to sequence the full genome, the full human genome, that is. So you see, technology can make a real impact there as well. We are trying to understand the brain. Here is the new standard for doing brain research on rodents. It's the NeuroPix. It has the capacity and the capability to measure more than 6,000 neurons in parallel. And actually, if you look at the impactful papers, there's quite a few designers that are listed on this page because they make the difference in how to get these signals with the right signal-to-noise ratio from the cortex or the deep brain to your computer. And some of them are in the audience here even. So we see as design community, as technology community, we can make quite a bit of difference. There is going to be an enormous amount of data that is going to be generated by this type of devices or systems. And actually, these data will be interpreted by other machines, again, from AI to AI, because the human interface is going to be too slow or not even precise enough to make decisions out of this very, very complex set of data. So it is pushing circuit design also to the extreme. And then as a final slide, to make sure that we capture the benefit of all this, again, here we need to bring the AI or the algorithms in general very, very close to the technology. We see use cases in monitoring our own life cycle and making sure that we stay on the right track, and maybe if the right track is to be left, that we have the best possible outcome with the therapies that we will manage to make more personal. And then, of course, also there will be process analytical tools needed to do the personal medication development that is going to be needed for the personalized medicine. Technology, use case, data, AI coming together. I think that's what we mentioned with the full stack innovation. That's where the opportunities lie, and not just for Europe, but that's where we're banking on. And it's a call for, of course, again, system technology co-optimization. I think I said it 25 times now. Pilot lines and design platforms coming close together so that your community can talk to the technologists and that both of us can talk to the use case. Focus on sustainability. Again, the panel later today, and building, please, building the talent and the skills, because otherwise it'll be an old boys club soon. Full stack innovation and partnerships. Thanks for the partnership to bring this paper to bear. Thanks again also for the opportunity and for coming back to the audience here. Thank you so much.
Thank you, Jo. Thank you, Jo, for this excellent talk. So we move on to the final speaker of this session, which is given by Erik Ekudden, Senior Vice President and CTO of Ericsson. He will talk about 5G, and he will show how 5G is a driver for various industries. So as Ericsson's CTO, Erik is responsible for setting the overall group strategy and technology direction for Ericsson. His focus for the group is on strategic decisions and investments in 5G and 6G mobile systems, cloud, artificial intelligence, security, and Internet of Things. This builds on his decades-long career in technology strategies and industry activities with leading customers and partners. Erik first joined Ericsson in 1993, working on mobile systems, and rapidly moved into leadership within research and technology. He has served as Research Area Director and Vice President of Technology Strategy, Standardization and Industry. He also mastered a Master's of Science degree in Electrical Engineering from the Royal Institute of Technology in Stockholm, Sweden, and he is a member of the Royal Swedish Academy of Engineering Sciences. Welcome, Erik.
Thank you, Pete. And good morning, everyone. This talk is going to be about the mobile industry, the mobile network part of the mobile industry specifically, and where we are today and the coming 10 years. A little bit of an outlook, but also taking stock of where we are. But it will also be about some of the challenges that we are facing, and I think they can be addressed by this distinguished ISSCC community for sure. So it's a little bit of a call out to all of you as well, because this part of the industry, the mobile network industry, it has a tremendous opportunity when it comes to how we use networks, but it also has some pretty daunting requirements on us when it comes to energy efficiency, when it comes to even more bridging the distance between the devices, the sensors, and of course, the cloud servers. And that's really what the industry is about, bridging distance, reducing latency, making sure that we do it energy efficient, and of course, keeping up with the data demands from all the applications and the users. Let me just check here, a show of hands. How many are in the mobile network or wireless areas? Can we see some hands here? It's 10%, maybe 20%, something like that. So for all of you, some of this will not be entirely new, but I will talk also about what we need for the coming 10 years, and there, of course, much more of the research challenges. And to the point of the title of this talk, what we see now as we build the network platform, we build the digital infrastructure in between devices and applications, we really fuel not just the innovation, but the demand for compute also on those two sides, on the device, on the cloud side. So a few numbers about Ericsson, key figures. I would say this is to a large extent representative for the whole mobile network industry, but I'll take Ericsson as an example here. So 75 billion gates. That's really what a connection from basically the interconnect point, the core, the RAN, into over-the-air interface, into the device chipset. That's really what the connectivity path touches, 75 billion gates today in early 5G. And a big part, a large majority of that is on the network infrastructure side. Then, of course, there is some 10-15% on the device side, but this is really about network processing needs. And it's just going up, as I will show you. And then when it comes to node technology, yes, we are, of course, on the leading edge when it comes to 7 nanometers, 5 nanometers, moving to 3 nanometers in FinFET and surround gate, or gate surround. But what we are also realizing is that this is not the only way for us to scale. And Lisa was into it this morning. This is much more about architectural principles for us, but it's also very much about the relatively low scale that we have in terms of chips that we put into the infrastructure. If you compare to the device industry, the laptops, or even just the server industry, of course, we are at a much smaller scale. So we have to be smarter about how we build these systems, architecturally, as well as leveraging heterogeneous architectures. The 120 decibels, that's dynamic range. And if you think about the difference between that faint signal from the remote sensor compared to that watt transmitter just next to you, that 120 dB dynamic range is really needed. And that puts some extra requirements on us on the A to D DJ, but also the signal processing compensation for imperfections in the chain. In fact, this is an area where we have to have very dynamic precision, so 24 bits at some points, and of course much less in others. And the more than 10 gigasamples per second, that's really because we want to combine a number of bands, do processing over basically everything up to 5 gigahertz in one go, or if we're talking about higher frequencies like 28, 39 gigahertz, of course, we want to have a bandwidth of roughly 2 gigahertz. And of course, that requires these kind of sample rates, and it's going up very quickly, actually. And it was well covered in an earlier talk here as well, why this is a critical part of the system. From an Ericsson point of view, we are delivering 5G networks now all around the world. Actually, around 140 of those networks are live with Ericsson gear, and that really shows how critically important it is to have your own development of silicon ASICs as a part of this offering, because that gives better energy efficiency, that gives better performance in terms of uplink, that gives better performance in terms of capturing all this data growth that come from 5G devices. And it fits into a network infrastructure, of course. Starting on the radio side, I already mentioned that this is where we talk about the high bandwidth and the needs from not just the PAs and the ADDA, but actually the front-end compensation. That is consuming a lot of those gates, actually moving all the processing from central baseband into radios. That means that the radios need advanced ASICs, and then I will come back to that in a moment. Is of course the baseband processing, where it's much more about shared resources and using that compute cluster to process hundreds, if not thousands, of sessions at the same time. And transport, that goes without saying, is a big consumer of advanced technology as well. And all of this is really, of course, connected to advanced network functions, software, AI-driven more and more, that makes best use of the hardware. And if you think of it, this combination of a very dedicated hardware that is energy efficient, but also really tailored to the needs of every device, combined with advanced AI and automation software, it becomes a very complicated, very advanced distributed system that needs to be managed in lockstep between the hardware and software. And that's, of course, also one of the reasons that we have to continue to push the boundaries when it comes to our own ASICs, when it comes to hardware that solves this integrated with the software. Now, some of us have been in the industry for a very long time. If you look back at the 30 years that has passed, from 1990, where we basically started with digital mobile systems, digital communication. And it was about voice call, of course, and text messages. And every 10 years, we have increased the data rates by around factor of 100. So we have now achieved 1 million times higher data speeds in wide area networks, in mobile systems, compared to 1990. So from around 5 to 10 kilobit per second to similarly 5 to 10 gigabit per second today. And that is, of course, a very fast pace in terms of technology development and innovation. And as we heard from Lisa earlier today, this, of course, beats roughly 2 times every 2 years. But on the other hand, we were helped by increasing also the spectrum. So we're using more and more spectrum. But even so, this is an important data point. So we are moving at a very rapid pace when it comes to not only handling the peak rates, as this number shows, reducing the latency, reducing the energy consumption, overall bringing an even more efficient communication system. And that, of course, is really the starting point for where we are today. When 5G now is not only used by smartphones, how many 5G smartphone subscriptions do we have now, end of 2022? About 1 billion 5G subscriptions have already been rolled out. And in the coming 5 years, we will see another 4 billion. So 5 billion 5G subscriptions in just 5 years' time. So it's really moving at a very fast pace. But that also means that the smartphones is just one part of the 5G ecosystem. The rest is really the connected devices, the sensors, smart enterprise connectivity that goes beyond just your local connectivity. It really becomes part of that distributed infrastructure. And when it does, of course, it changes the way we do work, not just in wide area systems like the fire truck or the ambulance here, using network slice technology to have the right quality of service for that session, the right security, the right latency, and so forth, the right bandwidth. But it changes every other industry sector as well, because you can build on, you can leverage this phenomenal technology that has global reach, but also have the performance and the cost advantage of this system. And this is really where we are today. Going into the enterprise space, you see examples from, as I said, transportation, where basically all public safety now is moving to 5G. You see that in rail, you see that in utilities, you see that also in smart factories, for example. So our own factory, where we're building 5G, there, by using this wireless technology from day one, when you build a greenfield factory, you can reduce energy by 25%, you can reduce water waste by 75%, you can get double the productivity per employee by using this technology in AGVs, in inspections, in your AR glasses, but of course also in the regular connectivity on site. And that's just showing that this is going to happen over the coming 5 to 10 years, a massive transition into using the network more as a platform, more as a service for every enterprise, for small, medium businesses all the way to the large enterprises. And that's a good thing, of course, because the industry needs this scale to be able to continue the innovation. the industry also needs to reach out, because now we are changing how you're building things, not just in the communication and connectivity space. You're changing things in terms of automation and processes all across the digital stack. And that's really where partnerships comes in. It doesn't work to do it all alone. It really requires all of us to work together. So what's next? What's going to happen over the coming 10 years? Well, I see that we have a chance, and we do have to work hard on it, but we do have a chance to continue this trajectory of 100 times higher performance in the coming 10 years. It's going to be a challenge, that's for sure. It's not going to be perhaps as easy as the previous 30 years, but it is certainly doable. And it's a combination of really advanced signal processing, really advanced antenna systems, but also, of course, some more spectrum to go with that. And the higher up we go in spectrum, the more complicated it becomes for the compute part as well. And that's something that we need to sort of battle with at the same time. The 4 areas that we believe are most important when it comes to 6G is really to look at this unlimited connectivity or communication, which means that we need to get indoor, we need to get to satellite, we need to get to wide area beyond today's terrestrial systems. But it also means, as I've said before, energy efficiency. We have to break the energy curve. We have to basically stay at the energy consumption that we have today, despite the continuous exponential growth of traffic in the networks. We have to bring the compute into the networks much more than today's edge compute, which is really only at the edge, so to say. We need to bring the compute part even further out in the radio network. And certainly we need to build trust in this infrastructure by security. Hardware security was mentioned already before, and Ingrid got well-deserved recognition for that. This is absolutely critical, to build in hardware security from day one when we go towards 5G Advanced and 6G. And then the last part is, of course, the automation. Automation and AI is already paving its way into the digital infrastructure. We are really touching the surface of that, or scratching the surface of that, with AI-driven automation for how to run networks. But over the coming 5 to 10 years, we will build AI capabilities at all layers, including at the lowest level of the base station. There, of course, the inference will require less precision. A few bits of the precision would be enough there, but this whole scale, this range of capabilities that then will permeate in the digital infrastructure, including the radio network, will be a key driver for 6G. In fact, we will combine this unlimited connectivity of the wireless part with the cognitive network, or the AI part, that already is starting to happen. So those 2 pieces will have to advance at the same time when we go into 6G. 2 other very important areas, and this shouldn't come as a surprise, but we are connecting sensors today, but those sensors still need to be charged. They still need a battery. They still need to operate with some kind of maintenance. And when we look at 6G, this is really where we see the opportunity to completely remove the batteries or make them energy harvesting. And one good example of that is the work that we're doing together with MIT here, where we are showing that in a 6G context, we can actually, through the same framework, what 6G will cover, we can start to capture the opportunities that comes from energy harvesting sensors. And that's partly possible already today, but not on a wide area scale. So over the coming 5 to 10 years, I think we'll see the development that will allow that to be part, full-fledged citizens on the 6G network with security. Of course, many other constraints will have to be there, but still it's a part of that 6G vision that we're working on right now. The other part, which is also to some extent connected to the energy efficiency that I mentioned, but it's also connected to this unlimited connectivity. We need to get really good performance everywhere. And what that means is indoor systems, as I mentioned, is to go beyond today's terrestrial macro systems into even satellite systems. And of course, that gives new requirements also on the compute as well as the signal processing part. This is where latency, coming down to sub-milliseconds and closing this divide between the physical and the digital world in the cyber-physical continuum, will have to come together. Today, we are expecting the lightweight AR glasses in just a few years' time to be more readily available. But when we go towards 2030, we see that we need to provide much more support from the network side, basically running all or a large majority of all the compute on the network side, creating that immersive experience. So that's a little bit about the journey. We have had this fantastic run for 30 years. We are continuing on the same path over the coming 10 years. The innovation continues towards 6G. But as I said, it doesn't come without really turning every stone to get to another 100 times in the coming 10 years. I mentioned a little bit about data. So how much is data growing in today's network? Well, it's actually continuing to skyrocket. And today, a large part of that is video, of course, downlink heavy. This is really where you have 70% or so in most networks are video, downlink heavy. And you can see on the left-hand graph here that, and this is a prediction out until 2028, so the coming 5 years. You can see the yellow part here is showing the traditional or now legacy mobile data systems from 4G, 3G, 2G, tapering off and basically going down in the outer years. You see the growing part of 5G mobile data, really growing to be the majority already in we could say 3 years. Around 3 years, you would start to see that it is coming to be at the same level or even increasing. And then you see the purple even being more than the legacy system. And then you see the purple part here. And what is that? Well, as I mentioned, if you have this scalable technology that works all around the world, and it works both outdoor, indoor, when you have mid-band or roughly 3.5 gigahertz spectrum to use for 5G. You're not only using the rebanded low bands, you're not only using the high bands around 20 to 30 gigahertz, you're using these mid-bands between 3 and 4 or 3 and 6 gigahertz. Then you get this fantastic capacity that allows you not only to get good smartphone experience, but is good enough for fixed wireless access. So you can actually start to replace the residential access or the, as I mentioned before, the small, medium businesses access with wireless technology. Getting that flexibility so that you don't have to dig fiber to every endpoint, to every home, but you can actually start to leverage the technology at a cost-efficient manner to serve also really demanding, high-demand customers that have SLAs that needs to be honored, but also that start to tap into the enterprise usage. So remote worker over the last 2 to 3 years is a norm, and I think we will be able to serve that usage pattern over the coming years through fixed wireless access. And as you can see here, in the outer year, it's a very substantial part of the network. And for those of you in wireless and in network dimensioning, you know very well that once you start to get to fixed devices, fixed endpoints, the whole dimensioning changes. That's really where you need to start to have super advanced beamforming. You need to be very smart about the scheduling, but you also need to look at the patterns, the usage pattern of these fixed points, very, very different from the mobile that roam around. So for the whole industry, making sure to cover both the use cases of full mobility, wide area mobility, as well as local or directed connectivity, directed access to fixed points or fixed places, that's going to be really critical in the outer year here. But again, some of us already enjoy these services. This is becoming technically, commercially feasible and is really skyrocketing on that part. The right-hand side, it really shows how this will evolve around the world. So coverage by existing technologies, 4G, 3G, 2G, is already at the 95% population coverage worldwide. Doesn't mean that everyone is using it. As you all know, we have a digital divide that we need to close. That's more on the device and the literacy side. But when it comes to having coverage, is around 95% population coverage around the world. But then you see the orange curve here, where very rapidly 5G coverage will be built out, basically offering this connectivity layer that serves them both consumers and enterprises, reaching more than 80-85% in the outer years. It's only 5 years from now. So that's a little bit about the industry, where we are in the coming 5 to 10 years. Is 5G then a driver for compute need, or is it enough with standard CPUs? Is it enough with the capability that we can basically buy off the shelf? Well, I think Lisa was into it very much this morning. It's certainly not enough for 5G today, and if you look at 5G Advanced and 6G, even more pronounced the needs to have unique ASICs, to have tailor-made and heterogeneous compute capability along the chain. And this is really showing how the trend, or rather the numbers from 2010, roughly, where we introduced previous technology for the LTE to the left until today, 2020, roughly. And you see the different colors here. At the bottom here, it's about radio control and packet processing functions and layer 2 processing, while the green, orange, and black one is layer 1 beamforming and digital front-end processing. So going back 10 years, we used to have a 20 megahertz carrier. We used to have maybe 2 transmit and 2 receive antennas, and we were talking about doing all the processing in a millisecond. Fast forward to where we are today. Now we're talking about 100 megahertz carriers, at least, and I mentioned carrier aggregation before. We're talking about 64 transmit and 64 receive for a macro system, and we're talking about doing that processing 160 times more processing in half the time. So of course, this cannot be done cost or energy efficient without having unique hardware. And this is really where the Ericsson silicon comes in, and this is where the whole industry is now investing in making sure that we can cover this compute need in the most efficient way. And it's actually just continuing in this way. And the reasons are obvious. One is to keep up with the data, but also, as I mentioned, we are talking about multi-band systems. We are using wider bandwidth PAs and wider bandwidth systems to be able to carry aggregate between a number of low bands, but we also have more bands coming up in the mid and high band range. And of course, that requires wider bandwidth and therefore even more than the 100 megahertz indicated here. So is this good news? Well, I think it is good news in many ways, but it's also very challenging because this processing cannot be done remotely. This processing needs to be done distributed and very, very air interface near. And that, of course, put extra requirements that cannot be shared. This is compute that is more or less dedicated in the radios, in the antennas, all the way out on the site. But at the same time, this is really the way to drive energy efficiency, drive higher uplink performance. I mentioned before that one of the key requirements now when we move away from consumers and the downlink heavy traffic patterns into more uplink balanced scenarios with XR, with immersive experience, where you are moving some of the workloads from the smartphone, from the glasses into the network edge, then of course the uplink becomes so much more important. And to be able to do good uplink performance, you need to do the processing very air interface near. You need to do all of this processing in the radio. It cannot be done centrally, it cannot be done on the baseband. So it is a necessary step, but also a very, I think, important step in order to keep up with the demands here. And this is really why this comes together in a unique family we call Ericsson Silicon that handles a range of ASICs from very, very radio near all the way to baseband and centrally. So for those of you who are perhaps less into mobile macro infrastructure, why do we need to go down this path? Why don't we just have smaller cells? Why don't we just densify the network and get rid of some of these challenges? Well, first of all, it doesn't really scale. We need coverage in the system to bring down the cost of the infrastructure. That's still true. And that coverage needs to be as big as possible, which of course means advanced beamforming for the mid and high bands. But that coverage then requires us to handle the very sort of big dynamic range, 120 dB, as I mentioned. To be able to listen to that faint cell edge device, the sensor, and at the same time being able to block out that what transmitter next to you or on the same site. That really requires the latest hardware on that side. Users, of course, if you have large cells, you have many users in the cell. That in itself is a demand, and these users have higher and higher demands on the network. Absolutely clear when it comes to new usage pattern, XR being the obvious example now, which drives in itself the need for higher bit rate, and those bit rates, of course, means that we are using more of the spectrum. We need dynamic spectrum sharing, we need advanced usage of both the mid-band, the low band, and the high band. And that spectrum that needs to connect it is not enough today. We need to continue to drive towards higher bands, and when we go to higher bands, of course, signal performance or the performance in general means that we need to compensate even more on the silicon side. And that in itself, coming back to the coverage, need big coverage sites, becomes a virtuous circle here. For every generation, for every step we're taking here, it just continues in this way. And then, what about the other parts here? If this is the network evolution, there we are talking about the drivers for the network to involve or to improve. Combining that with the development on the device side, of course, we already see much of that in the XR space with AR and VR glasses, but even more so in the connected enterprises, the advanced automated drone deliveries, all the things that will be wide area autonomous systems. And then combining that with the full application suite, being able to really do everything over that one network. It becomes the same needs that we now need to fulfill on the network side. Higher performance, lower latency, higher energy efficiency. Those very same needs then are prevalent, of course, on the cloud and device side as well. But it doesn't come without thinking about this end-to-end. So while we previously, and certainly during the 4G era, took for granted that we can handle the connectivity at the right cost, at the right price, just connecting a device ecosystem and connecting a cloud ecosystem, now we're talking much more about opening up the networks, being able to run it in some parts on-premise, in other cases for macro systems, making it open and programmable. Of course, that's a big change in the industry as such. Puts new requirements both on the hardware and the software, but also the openness towards partners in this space. And while we today see great momentum around the smartphones and the early enterprises, this is a journey that cannot be done alone. This really has to be done cooperatively across industries. And I think this is really where the coming 10 years will show whether we are on the right track or not. Can we work together across hardware, software, automation? Can we work across industry and sectors? Because now we are moving this 5G Advanced and 6G infrastructure to be fundamental for societal functions, meaning we're going to critical infrastructure, we're going to cases which are much, much higher in demand than today's system. And we do think that we can do that, but only by working together. So then, finally, what does this take in terms of hardware? What does this take in terms of what we can do here, what the community here really needs to do? Well, first of all, it's very much about looking at the requirements, specific requirements for mobile infrastructure, which are different. The distributed infrastructure, as Lisa was into in the morning here, will put higher requirement on tailor-made systems. But it's also about enhanced network performance. It's about this uplink performance enhancements. It's about dynamic spectrum sharing, all of these things that needs to be done very radio near. And as I already mentioned, we are breaking the energy curve, meaning that from now on, we can no longer, for introducing new technology in the network, we cannot increase the total energy consumption. In fact, with 5G, with the kind of deep sleep or the lean carrier concept, we are already breaking the energy curve, so we are not increasing the energy despite the traffic growing with more than 40% per year. But going forward, of course, we need to get that curve down, and of course, over time, we'll get it to zero with a total commitment on CO2. But as we do this, we are building new capabilities into the distributed infrastructure. And part of that is really the security, the hardware security at the core of this, at the core of every chip, but also at the core of the digital infrastructure. We have the capabilities now, and this is what we build in from scratch to have hardware security, but we also have a need from these other industries, the enterprise side, to be able to secure infrastructure from hardware, software, and of course the AI and automation on top. So, what is the takeaway then for this group, or for this community? I would say that if we look at the coming 10 years, we have the challenge, but also the opportunity to continue on the path of 100 times more every 10 years. Latency will be important. Energy efficiency will be super important. But we also have the opportunity to expand and use this capability across these other sectors, whether it's in the sensors, whether it's in the the sensing part of the infrastructure, or whether it's in terms of the applications that can be network aware and therefore optimized together with the network. This opportunity, I think, is in front of us now. Think of it in a similar way as a smartphone journey over the last 10, perhaps 15 years. The cloud transition, the app economy, all of those things are now available as base capabilities to the society, to small, medium businesses, to enterprises. And as such, of course, it will drive even more need on the network. But that can be done, I believe, by looking at the opportunities of innovation also on the network side, similar to how we looked at it on the cloud side and on the device side. And that actually means that I'm going to end here, and hopefully we have created some more interest in the innovation in the network infrastructure part as such. This chip is, this is where we on the baseband side are more than 40 billion gates. If you look at the radio near side, we are at 13 plus billion gates. So of course, there's a lot of capability that needs to go into today's and of course next generation systems. So with that, thank you.
So thank you very much indeed. It is time to close the session. I would like to invite the plenary speakers to the podium for a small token of recognition. Can we advance this one? So, Pete, the first recognition will be for Lisa Su. Pete Vanbach will accept it in her name. Matsuzawa-san, please. Your the book, please. And last, not the least, Erik, Ekudden.